All right. Hello, everyone. Sorry to interrupt you while you're tweeting or something. I promise I won't do that like more than half an hour, so you can come back to it. Yeah, exactly. Do change your password. So who has actually come to the other talk on chaos engineering on Wednesday, just to have a... OK, good. So I'll try to not rephrase everything I said. It would be a bit, useless. But I'll have to rehash a few things we saw the other day. So today we're going, and my name is Sylvain Hellegouarch. I'm only saying my name because it's not easy to pronounce. I'm not sure you'll be able. So just, call me Sylvain. That would be easier. Yep, don't go away. We're going to talk today about chaos engineering with the Chaos Toolkit. So I'll focus the first, part of the discussion on chaos engineering in general. Why chaos engineering, or at least how becoming a chaos engineer, the mindset and things like that. It's half an hour, so obviously it's not a full workshop on the thing. So forgive me if I forget something, but do ask questions at the end or come to see me after that. The subtitle of this talk is Proactive Reliability Validation, because we're trying to remain reliable. Have reliable system in our life, right? That's the goal. Resiliency is part of it, availability, safety, and all of those things, security. But really what we want is reliability, because our system is reliable, means that our users trust us and will use our system. I'm not sure the password thing is going to impact Twitter or not, but certainly not a good thing. Right, a quick reminder. So chaos engineering starts with our complex system. I bet for those who have been in the game for a long time, years ago, you were able to actually go to the mainframe or the machine, whatever, install your system, and your system was basically one binary and a few rules on Linux, on things like that. Today, it's not that at all. Your machines are so far away, even if it's not virtualized, even if it's you have your own data center, it's so far away, so complex, so remote that having a full picture end-to-end of your system is almost impossible. So you need a tool or discipline or practice, we'll see how it's been called, that will help you collecting data for you to remain sane in face of that complexity. Only by collecting data, you'll get the full picture of what's happening, or at least a partial one. Not just based on intuitions and hunches, but real data. Practicing edge cases in controlled manner is the goal of chaos engineering, right? It's not going and breaking stuff randomly without people knowing. This is not it. If you do that, your team is going to be pissed off. You will never learn anything. So that's not the point. Breaking stuff is one thing, and you don't really have to actually break anything if you want to learn from chaos engineering anyway. It's just one aspect of it. But you need to do that in a controlled manner. That means you tell your colleagues you're going to perform an experiment that will break something, or that will tear down something, or change the system in some manner, so that your teammates, first of all, aren't surprised and pissed off at you, and second of all, they will learn because they'll see that didn't catch something in the first place. So what is a chaos engineering mindset? Well, it's not a rock star. I don't know, in teams sometimes we get caught up in the rock star attitude of we need that person. No, it's not that. A chaos engineer needs to be quite far. It's not the person who is going to save the day, but is going to help the team save the day. So be open-minded. Try to not forget your experience, but remove the prejudice you have. We'll do that. We have egos, we have experience, and we come and say, nah, you don't know what you're doing. If you approach this way, people will not learn because they'll shut down immediately. So don't do that. Nurture empathy. Empathy is really, really at the core of chaos engineering. If you have empathy for the system, for your users, for your teammates, they're trying all to do the right thing. Your teammates are not trying to do the bad thing, but sometimes they struggle. So you're here to actually help them get there. Yeah, don't blame or be snarky. That never helps anyone. Love an experimental approach. And that's the third really characteristic. I'm not going to list many of them, just 3. Don't be scared of not knowing the outcome. Again, allow yourself not knowing. And it's probably not something we do very well in our industry. We always think we know what's going to happen, or we know the response. Well, forget about that. Try to accept that you don't know, and you're going to try something to learn from it. That's really the fun of the game, actually. If you allow yourself to learn, it's going to be much more fun. So those three things, to me, are the core of a good chaos engineer. If you have open-minded, if you are in the empathy of your teammates, users, and everything surrounding you, and basically, you love the experimental approach, you're going to have fun as a chaos engineer. And your teammates will really thank you. If you forget this, people will see you as the annoying guy, an annoying person, the one who's breaking stuff all the time that really doesn't help anyone. So try to be, in those positive mindset, if you will. So now let's talk about the chaos engineering workflow. Again, I know I'm going very fast, so don't hesitate to come back after, at the end and come and just have the discussion. So this is very simplified. I'm terrible at diagrams, so I drew what I could. But that's the gist of it. We need an hypothesis, right? We need a steady state. We need to define, and I'll come back to that later, I'll explain, but we need to define that. What that represents is where we are now, right? If we don't have a baseline, we can't learn anything because we don't see a deviation from the baseline. So we need that baseline. Now, once we agree that we have that baseline and it's there, because there is no point in trying to learning from a system that is already broken, you're not helping yourself, you're going to apply a method. Now, it sounds very scientific. It's not really a scientific, but we like the idea of the philosophy of the scientific approach. So the method here is just a bunch of actions you're going to run against your system. Now, if at the end you replay the hypothesis and the steady state is not normal, that means your system has changed based on the conditions you've imposed, then you probably have discovered something. Either your steady state hypothesis is wrong, good, you asked the wrong question, or you asked the right question, but you discovered something. That something now needs to be discussed within the team. Is it a real weakness? It's something the business should care for. Maybe having passwords for Twitter in log files is not actually a business problem, or is it? Now, that's the kind of question you would ask once you have discovered the weakness. You just don't go around and say, I found a weakness. No, I wouldn't help anyone. You prioritize, you order your weaknesses. Some of them you will agree that it's an old system that is going to be replaced because we're working on a different one now, so don't forget, don't worry about it. Now, if it's a security breach, probably you want to pay more attention. So basically, you do that in a loop continuously, and that's an important one. You continuously do that, and that's why it's different from disaster recovery, which usually disaster recovery is done once every blue moon, and basically it's done whenever it can be done. It's heavy, and it's very imposing on the team and the older structure. Chaos engineering is more, it's a flow, really. You do that like you do testing, which I hope you do. And if you do testing, then you can move to chaos engineering. Otherwise, start with testing. And chaos engineering is fairly different from testing. Testing, you know where you're going. It's a fairly binary thing. Is it there or is it not? Chaos engineering, it's an open question. You're trying to learn something. You forgot your prejudice, right? So the mindset is different, even if the tooling will probably look fairly the same to you. Steady state. So let's come back to that. It's a normality in your system. What your system is when it's normal. For example, it's a made-up steady state here. But customers spend X amount of dollars or euros or whatever at 8 a.m. on average. Now that's the thing the business cares for. It doesn't. No one cares for your service going down, your resiliency, all of that. What the business cares is that this remains true whatever you roll out, whatever you do. You don't want to change that, at least not in a negative way. If you do, then you've learned that something went wrong. So that's where you start. But let's roll back. Can you make, because we now have a normal position, we have a baseline, but can we make an hypothesis? It's not actually easy. You don't know. You don't know what you don't know, right? So you first ask questions. Sometimes you have an intuition that this thing will actually impact the system in some fashion, right? So that's a question you ask as a team. What could go wrong that would impact that baseline? And even before that, you may not even have a question. So collect data, have metrics, and start analyzing your metrics and make sense of them and figure out things you don't know. You probably have dashboards, fantastic dashboards, that you may or may not look on a daily basis. But I'm sure you look at them and you're like, they don't actually tell me what's up with my system. I will know when it happens. I will probably see that the response time is going down when it goes down. But it's too late at that time. So even if you have dashboards, sometimes they don't actually tell you in advance what you're looking for. And by practicing chaos engineering, you force that to happen before it happens in real life with your users. And you learn and you fix, it's positive. So your hypothesis, it's a statement that should be proved or disproved, usually to detect a weakness in your system, but also you could use it to predict an outcome. So for example, let's say we have services that manage the payments. And I'm using that based on on Monzo the other day on the Monzo keynote, which was fantastic. So let's say you have like 10 services, and you're going to do a rollout. And within that rollout, you say, I'm going to kill 5 of them, which will be replaced, and I'll keep 5 of the others, and I'll do the rollout like that. So does this decrease the average spending? And that's a question you want to prove or disprove. It doesn't have to be business-oriented. It's obviously more interesting and more forceful. And you can go back to your managers because they understand that, not necessarily your metrics. But because chaos engineering can be at various levels, you can also have obviously very engineering hypotheses that you keep for yourself or your team. The experimental method, now that you know what you're looking for, you know where you're starting, you know what the question you have, what are you going to change to actually make that happen, to see if you can prove or disprove. That you're going to vary things. So basically, you're going to perform a rollout, or you're going to kill pods, or whatever is necessary to sort of prove, disprove, or at least gain some knowledge of your system. Sometimes you'll have to do that many times because what you vary doesn't actually impact the thing you're trying to prove. Now, it doesn't mean that it's safe. It means maybe that you're not changing the right thing. Scale down the payment service by half and query Prometheus for number of payment enderment during that period. That would be an experimental method to actually see if that proves or not the system is sane. But don't vary too many things because you won't be able to make sense of any of it. So have discrete experiments as best as you can. In summary, a chaos engineer demonstrates great empathy, again, very important, for users, teams, and the system. And the system, I'm inclined here to insist on the system. You may come on a legacy system that you hate, you dislike, because it's in your mind of good engineers, you think that it should be done this way or this way. That's not a problem here. You have a system in front of you, and you need to make sense of it. And by observing the system, you start asking questions that turn into an experiment that you can play automatically and just learn from your system. We saw that. The probing is important here because you collect data as you go. You may have monitoring, but for the purpose of the experiment, you may also collect data on the side that are not necessarily based on your monitoring. And you look if the system deviated. And if it did, again, you may have started, you may start the analysis with your teammate. So now that was a very, very, very short and all too brief, overview of chaos engineering and how you could develop that mindset. Again, come back to me after that and we can chit-chat on this. Now we're going to see one tool that could actually help you on doing that. It's called Chaos Toolkit. It's an open source one, and it implements the flow that we just described. So what you do is you describe in a Chaos Toolkit an experiment. You have your steady state, the hypothesis, the method, and that just replaces it. It was born in recently, so it's a fairly small project, fairly dynamic in the sense where things are happening, but it's not well established yet. But it accepts contributors. It has nice community. We value very much the friendliness of the community. It may be small, but we're all very we try to be friendly together. We don't want to be snarky at each other, saying, you should be doing this way or shouldn't that way or things like that. If a user arriving on the project fails to understand something, it's because the documentation is wrong or something is not well explained. So that's where we're starting from. And it's implemented in Python. Yay! I'm sorry for all the Golang users, but you gotta succeed. So, and the functional approach is, I'm not saying Python is functional, but the way we've designed it is the idea is to keep a very simple approach of functions with input that are as immutable as we can, returning something. That really helps the development of the speed development of the toolkit. The core objective of the toolkit, we try to be the entry point of the chaos engineering experiment. What that means is really when we started it, we realized there are many tools out there, but they aren't easy. If you tried Chaos Monkey, just even setting up requires quite a bit, right? It's not something you can grab and just run. So if you haven't got the time, the mindset, then it's quite involved. Chaos Toolkit tries to be the opposite, tries hopefully to be as simple as you can, but still learn quickly from it. So simplicity is a key for durability in software, in my opinion. If you're simple, then things can change fairly, naturally. If you become complicated or complex, then your software is doomed to have many problems down the road. We interface with platforms and systems natively. So what that means is there are plenty of tools, like I said, doing chaos, injecting faults in your system already, like the Chaos Monkey, Gremlin, Pumbaa, all, Power Seals, many tools. But so we thought, well, we're not going to rewrite that. That would be foolish. We're going to drive them, because that's really what matters is the simplicity of getting them started. So, and we quickly realized you can do a lot already by just talking to actually the system. Terminating a pod, you don't have to go and do fancy things to actually terminate a pod. You call terminate pod the delete, function, the delete method on the pod at the HTTP level, and you're done. You've actually terminated the pod. So there's not much, you need to do and fancy, engineering here. So we prefer extending as much as we can. We are declarative, and I'll show that later on. That means you don't necessarily have to actually code anything. You can just declare your experiment, a bit like Terraform tries to do. Automation first-class citizen, so it's a CLI for now. You won't have any UI. You don't have to click buttons. What you have is you describe that in your experiment somewhere, in a file in GitHub, so you can share that, review, blah, blah, blah. And then you can run that from any CI you want, or anywhere, basically. And like I said, be a friendly project community. So roughly, because again, I'm not very good at diagrams, but this is where we stand. The Chaos Toolkit is in front of all those systems, or all those providers, if you will. And we just use them to, to inject some problems in your system. So there are others right there. And the plugins are merely, extending the toolkit for new functions. Wow. So this one is how it works. We have a core, we have a library, and it calls those APIs. So I'm going to show you that in demos that will be more interesting. Experiment. So it's an open API. So what we did, we thought, well, we're going to declare an API, because who doesn't do that? We all like a spec. And we're going to try to do that before we code anything. And we're going to implement the spec first, write the spec first and implement that after that. The spec is declared using JSON, but we tolerate YAML people. No, I'm kidding. Basically, it's you can declare in any of those. It doesn't really matter to the toolkit itself. It just loads that into a dictionary of some sort. Drivers, like I said, we drive the API, so I went for that. So usually drivers are implemented in their own repository projects, as in Python again. Like I said later on, we're trying to work on whether or not you can actually call like a Go or Rust or whatever you want. So call them from Python instead of just Python, because we understand that communities are various. Or you can even call processes. So sometimes, instead of writing code, you have a command line. Like we use Vegeta for load testing. I don't know if you're familiar with that. It's just a binary that takes a file and replays that under load to inject load into your system. It's very neat. And we thought, well, why would we wrap that into a Python code? Just call it. That's it. Right. We don't try to be clever with the extensions. When I say that is we don't try to create too much intelligence in one extension. We give the tools and you do as you please with them. With drivers like you saw for them. Plugins are just adding functionality so for notification and things like that. Not very interesting. So at that stage, what time is it? Yeah, I've got the time for the demo, more than the time. So at that stage, what I've done is really give you a quick tool. I know it's a bit boring probably at that stage. So I hope the demo will be more meaningful to you. All right. Up. OK, go away. Yeah. So where are you? Nah. We're going to run a demo against Kubernetes. Yeah, of course. And we're going to use Kubernetes on GKE. Could work on Minikube. It's just calling Kubernetes at that stage. There will be a demo specific to GKE if I have time, so we'll see that. On the right-hand side here, you've got Weave Scope. That's one of the products of Weave. So I don't know if you're familiar with that product. But Weave Scope is very neat if you need to see your system because it shows you real time the topology of your system, your Kubernetes pod services. So it's really helpful when you do something like that to actually have a view of what's going on in your system. And that's just the default alert dashboard for Prometheus. Now, what we're going to do is we have, where is it? Where are you? Hey. OK. That's not very clever, what I did. All right, so here we have an experiment. Again, it will be JSON this time, but you get the gist. It would be exactly the same in YAML. So what I'm going to go through that spec quickly so that you understand what we do. I'm sorry for those who hate DSL, but it's either that or your code in one language, and it makes it much easier with DSL to have extensions from various languages. So hopefully that don't put you off. So we have bits of metadata, not interesting. Go away. Here we've got the configuration and secrets. Now secrets aren't very secrets when they are like that, right? But that's a demo, and that's demo as a password so that you know it. But again, that's a demo, and I didn't want to actually burden the thing. But the idea here is you have configuration secrets. Secrets could be loaded from the environment or Vault. And if the community wants to contribute something like KMS, that will come as well. So the idea here is you describe your secrets. And because, again, Chaos Toolkit always trying to reuse what already exists, we don't have a secret management system. I would be foolish. So use Vault, use something else, or environment, that's fine. But we're just saying what you can load. A configuration are not secrets. It's similar to Kubernetes, right, at this stage. Now we have our steady state. So we have a title. And then we have those probes. Probes are just collecting data. But at the level of, and this one is not necessarily very powerful in that case, but anyway, we have what we call tolerance. A steady state will bail, when we start the experiment, will bail immediately if the system is not normal. There's no point, like I said, to even run this thing if it doesn't look normal. So that's a gatekeeper, if you will. And basically here, what we say is, are we using a different kind of provider? It's just HTTP. It's going to run that and see if that comes back with a 200. But you could have intolerance, a regex, a JSON path, thing like that. So you can go pretty wild with it. Blah, blah, blah. So it's going to do them one by one. And then here it's an interesting one because it's a different one. It's a Python one. So this one says, I'm going to use that module, and I'm going to use that function that is just, that is implemented in that module, and I'm going to use those arguments. So we pick up that function here through the label selector, and we're going to say we want one only. if there are two, and our system in that experiment is not normal. We wouldn't learn the right thing if that was the case. So see, we have a JSON pass here, so you can do something, more on the payload that is returned. Right, and the action is more interesting here. What we're going to use here in that experiment, the idea is to say, I want to see if OpenFast automatically scale out my function, basically my pod under the hood, when the load is increasing. That's a promise it makes, and I just want to see if that's the case. Now here, that demo is using bare OpenFast. I'm not judging OpenFast, and actually it does the right thing anyway, so that's fine, but you would have to tune OpenFast. I want to make that clear here. But the idea is we're going to inject some load. So we're going to use Vegeta to say attack the system. They all have to be called attack. I don't know why you want to attack a system, but it feels very, I don't know. But we're going to use that to send some load, and we're going to say we want that rate of for 50 seconds, I want 30 requests per second or something like that, and you spread that across 8 workers. Doesn't really matter how it works. And we're going to do that in the background, because obviously if we do that and wait for it to finish, we wouldn't learn either. So at that stage, in the method, we also have a probe that is going to simply fetch the alert. Here, we don't have a tolerance. Within a method, you're not testing things. You're not bailing at that stage. You're looking objectively what the system does. And that's the thing. You're not bailing immediately. You're trying to be as objective about the system reacting badly or well as you can. And then we have more probes here. And this one is just going to look for, just to have basically when we do reporting, we'll see how many pods were triggered. So without further ado, and here we could query Prometheus again. Let's run this. And we'll try to have visibility, observability as well, won't we? So back to Weave. And I really hope this is going to work. Come on. All right. So the way it works is fairly simple. It's called Chaos, so that you know exactly what you're doing, and run, and you basically take that JSON/YAML file. Alert, and it's called experiment. All right, so I would like you to pay attention. Unfortunately, I don't think this one refreshes, so I will refresh that one so that we can see what's happening. But this one should refresh itself automatically while the experiment is running. So let's hope that happens. Could you? Yeah. So the experiment will check the validity of the file itself as best it could, so it fails immediately if it doesn't work. And then it runs the experiment I just gave you. So it does exactly what we saw. We see that the load is arriving to the function. And basically, we're still waiting for OpenFast. Because OpenFast at this stage, come on. It's triggered on that, and because I was too slow, it should have been yellow and then red. But it sees the alert, so it triggers and creates new pods, new function instances. And we're still running, and because what we're interested in is, did we get the alert? Did it work? Things like that. That's the kind of things that we're interested in that experiment. So it's still red. And the load is spread across as nicely. So we continue doing that. Like I said earlier, it looks like testing tools. The tooling is fairly similar in that regard. But the mindset, again, is different. You're not trying to be binary here. You're just exploring what happens. And in this case, because I already have done the work, it's going to be green, unless demo gods are against me. But it should be green. But it would be red, saying that something was fishy and was deviated. I'll show you how it looks after that. So we see it came back to 1. And I think this one, come on. That's not what I want. It came back to green. And there you go. There you go. So for once, that worked. Good. So here you see clearly that the idea of the thing, we at the very bottom, we see steady state hypothesis is met, as we see at the beginning. Those are exactly, that's one that is run before and after. And you see if there was a deviation. So for example, it would be read immediately if it had deviated. It would tell you, this is not what you expected, right? And then you learn by looking at the report. Evans, I think. Oh, God. Alert report. Is that the right thing? Yeah. So that's a kind of report that is generated. And funnily, because my local is in French, that's the only thing that is in French in that. So I noticed to fix that. But that gives a slight touch of glamour. All right, so basically what it does, the report is fairly dumb in the sense where it doesn't magically tell you what you need to do, right? It gives you something you can share across the team and start learning from. It ideally, down the line, you would generate a temporary report, add your comments, add your analysis, and then send that across. Because we're using Pandoc, it can generate HTML, other things like Markdown or whatever. Now, the interesting bit here is, if that worked, sometimes it's a bit flaky on that one. We see it generates also graphs from data that was collected. Now, it's interesting because our steady state was just about whether or not we have one function there, one function instance. But we see that from the run, actually some connections failed. I guess during the time that we couldn't actually handle the load before it triggered, right? So you still have an analysis after the steady state, right? You see that basically what happened still impact the user. So either you come back to your steady state and make it more knowledgeable, or you simply make a statement, a confirmation with your team what happened. And sometimes you have to rerun that because it's not necessarily easy to actually grasp blah, blah, blah here. But the interesting one, I think, is, where is it? This one. So that's querying the number of function pods that we have. And we do see, it's easy to see that we went from 1 to 5 because OpenFast will add 5 of them dynamically, at least in the default configuration for now. So that's what we expected. And it came back to 1. Again, that's what I expected. Oh, what time is it? I think I'm done, right? I'm soon done. 3 minutes. So I want to show you the next demo. The other demo, that I'll come back to the talk, which is almost finished. The other demo you could find and come back to me after that is using JKE, where let's assume your nodes have your virtual machine nodes, not the Kubernetes ones exactly, but the machines where they live. The nodes have a security breach. You need to change something. In JCloud, it's easy to actually create a new node pool, bring it up, join the cluster, and swap to it. But have you done that? Have you ever done that in production in a manner where you feel confident of doing it? You may have, but usually it's more like, shit, I have to do that now. Is Easy here to do that, or is she here? So it's nice to have Chaos Engineering because that demo that I have, the other experiment, just does exactly that. You look, you set a steady state. You say, I don't want to disturb my users while I do that. And you run that. And that will basically create a new node pool, switch to it, and see if the users are still receiving the load. And I think that's pretty powerful. So I'll finish quickly with, if I can find, where are you? Yay! I will quick. Let's read. Yeah, it does that again. So for now, you'll see yeah, exactly, it's chaos. So let's it's just one slide anyway, I think. So what's next? Because Chaos Toolkit is a small and newer project, we have plenty of things we can look forward to. One of the things is, for now, you run that from an outside machine, which I think is the right thing to do, but sometimes you want to run that from Kubernetes itself. So we're going to look at CRDs and jobs and things like that. We need to improve the documentation a bit, because it's a bit messy right now. Again, we'll try to implement drivers so that you can do that in Go, in Rust, or however you want. We want to work on discoverable experiments, because it's nice if you could share experiments between between each other. Say, oh, you've got that system already, that kind of system. Can you send me your experiments? That would be very awesome. And obviously, trying to reach a 1.0 by the end of the year. And I think, yeah, thank you. Thank you very much.